In section 1.6, we look at the mathematical treatment of measurement results, and there's really two big things that we're going to do here. Is we're going to review what we mean by scientific notation, and then we're also going to run through a review of how we use conversion factors to achieve unit conversions. So we recognize that when numbers are either really big or really small, that when we write them, it's easy to make an error, and also when we read them, it can be easy to make an error because these numbers are going to have a lot of zeros in them. So these very big numbers, when we're dealing with macroscopic objects, sometimes in chemistry we're looking at something like, how many atoms are in a gram's worth of material. They're pretty common, as are very small numbers if we're looking at like the energy that is possessed by a single atom of hydrogen. So we have to get used to dealing with big numbers and small numbers without making errors. So one way around this is to use scientific notation to express these kinds of numbers. So in scientific notation, you always have a number that is multiplied by a power of 10. And the number has the characteristic that it has one digit and only one digit to the left of the decimal point. And that number is called the coefficient. And then the coefficient is always multiplied by a power of 10. If it's a big number, that's going to be a positive power of 10. If it's a small number, that's going to be a negative power of 10. And the power that we're raising 10 to, that's referred to as the exponent. And the power of 10, the whole thing, is referred to as the exponential term. So something to keep in mind about scientific notation is that in scientific notation, we only include significant figures in the coefficient. So if I look at this number here, you'll see that there are 3 leading zeros there that are not significant. The only digits that are significant are the 3 and the 4. So when I convert this number to scientific notation, I only include the 3 and the 4 in my coefficient. And as I mentioned previously, we only ever put one digit to the left of the decimal in our coefficient. So this number is written correctly in scientific notation. This number, while it's mathematically correct, that's not scientific notation because there are 2 digits to, there's no decimal point at all. And so yeah, it's just not scientific notation. Okay, so that's a quick review of scientific notation. Just kind of learn how to, enter scientific notation into your calculator or into whatever online program that you're going to be using. Make sure you can do that correctly. So now we move on to the section that's the major part of this chapter, which is concerned with unit conversions. So again, it's a very brief review of what we did in Chemistry 139. So it's important to realize that if we have 2 sets of units, we can write a relationship called an equality that relates those 2 sets of units. For example, when we write that 1 millimeter equals 10 to the minus 3 meters, that's an example of an equality. And you can probably recall that any equality relating 2 sets of units can be rearranged to give 2 conversion factors. And both of those conversion factors are going to be equal to 1. So if I divide both sides of this guy by 10 to the minus 3 meters, I would get that conversion factor. But if I divide both sides of that equality by 1 millimeter, then I get this conversion factor, right? So what you can see here is that by multiplying by either of these 2 conversion factors, a conversion factor is just a fraction, that's exactly the same as multiplying by 1. So I don't change the size of my measurement when I multiply by 1 or when I multiply by my conversion factor. What I do is change my units. So these fractions that we call conversion factors that are equal to 1, that's what we're going to be using to achieve our unit conversions. Where do we get these conversion factors from? We get them from these things called equalities. Some of these equalities we're going to memorize, like those 6 decimal prefixes. Others we're going to look up in tables. So whenever we use a conversion factor, we always make sure that we have the units that we wish to eliminate on the bottom line of our conversion factor and the units that we want in our answer in the top line of our conversion factor. So if I'm going to convert 1400 millimeters in meters, what I know is that I want to get rid of millimeters, so that goes on the bottom line, and I want to gain meters, so that goes on the top line. So my conversion factor is going to have the units I want on the top line every time and the units I want to get rid of on the bottom line every time. So now I've got my units established, I just have to think about how these guys are related. And what I know is that 1 millimeter is the same as 1 by 10 to the minus 3 meters. Right? Because milli means multiply by 10 to the minus 3. Now, normally we don't put the 1 times in there because we're lazy and we like to save space. So that's what's going on here. Here's my equality. And then I can reorganize that to get my conversion factor that has the units I want to eliminate on the bottom line and the units that I would like in my answer on the top line. And then finally, I multiply my measurement by that conversion factor. I cancel my units like that, and I make certain to take note that I only have what I want in my answer left over. The answer itself is given to the same number of significant figures as the number that I began with. Okay, now that's probably a little familiar to you, and most people are able to do sort of, a simple one-step unit conversion without too much fuss. Sometimes people have a little bit of a struggle with volume and area unit conversions, and the reason is that for volume unit conversions, you're going to have to cube your conversion factor, and for area unit conversions, you're going to have to square your conversion factor. So let me give you an example here. We're going to convert 1 cubic yard to cubic feet. Now I could draw a little diagram here and see how that works. So here's this cube. It is a 1 yard on each edge. So it is exactly 1 cubic yard. I know that 1 yard is 3 feet, so it is 3 foot on every edge. So if I wanted to calculate the volume of this, it would be 3 feet times by 3 feet times 3 feet, and that would be 27 feet cubed. But let's do this as a unit conversion problem. So we've got 1 yard cubed, and then our conversion factor is going to have yards on the bottom, feet on the top, and I know that I get 3 feet per 1 yard, but I have to remember to cube my conversion factor in order to get the correct answer. And you can see if I didn't cube that, I would have been out by a factor of 9. And there's very clearly more than 9 cubic feet in 1 cubic yard if I was to count all of those little cubes up there. Okay, so that's that. So here's another one, 1400 millimeters cubed in meters cubed. So I'm going to go 1400 millimeters cubed. Can put that in there. I know I have to cube my conversion factor, so let's do that before we forget. We want the units that we're getting rid of on the bottom line, and we want the units that we want on the top line. And so in 1 millimeter, there are 1 by 10 to the minus 3 meters. And so there I go. And then I just have to put that into my calculator and not make a mistake, right? Okay, so how does it end up? 1400 times by, parentheses, 1 by 10 to the minus 3, all to the power of 3, and that ends up being 1.4 by 10 to the minus 6 meters cubed. Okay, so we have to be careful there to cube our conversion factor. All right, so you get the idea, and if these were area unit conversion problems, we would be squaring our conversion factor. Sometimes when we're doing unit conversions, we'll have to put multiple conversion factors together in a sequence in order to achieve what we are wanting to do. A good example of that is when we're converting units involving time. So for example, if I wanted to convert 2 weeks into seconds, most people wouldn't know off the top of their heads how many seconds are in a week, and they would do something like this. They'd go 2 weeks, and then you go times, and you immediately put the fraction symbol, and you know that weeks are going to be on the bottom. And for most people, what they would know is that in 1 week there are 7 days, and then we would go again and we would put days on the bottom. And most people would know that in 1 day there are 24 hours, and then we would go again. We'll put hours on the bottom, and most people would know that there are 60 minutes in 1 hour. We're still not where we need to be. Then we would go again, and we want minutes on the bottom, and most people would know that there are 60 seconds in a minute. And you can see if we cancel out all of our units now, we end up with what we want. There we go. The only unit remaining are seconds. We know we should get a big number because there are a lot of seconds in a week. So 2 times 7 times 24 times 60 times 60. Now we're going to assume that that is an exact number, so we'll just write out the calculator answer without any rounding. It's pretty unlikely that there would be any uncertainty when we're counting the number of weeks that have passed. All right, so you can see there I had to use 1, 2, 3, 4 conversion factors in order to obtain this answer. All right. Sometimes we're going to have a unit that's a ratio, and common ratios in chemistry include things like speed, and they include things like concentrations, or sometimes like a rate of change, something happening per second, per hour, per day, things like that. So speed is the ratio of distance traveled in a given time, and you're probably familiar to this concept. And so this question asks us to convert 3 miles per hour into miles per second. And in this problem, what you're really doing is you're converting what's on the bottom line of your unit here. You're converting the hours into the seconds, but you're leaving the miles alone. So we need to know how hours and seconds are related. Here they are here. All right, 1 hour is 3,600 seconds. If you didn't know that, you would do 1 hour equals 60 minutes. And then you would do 1 minute equals 60 seconds, and you'd have to use a second conversion factor. So we've got 3 miles per 1 hour, that's our speed, and we want to turn the hours into seconds. So this time, the unit that we want to change is on the bottom line of our original unit. So our conversion factor has to have that unit on the top line, and then the unit that we want on the bottom line. So it's a little bit different, but the concept is the same. We need to make certain that the units that we want to change cancel out, and we leave behind the units that we want. So there we are able to achieve the conversion from miles per hour to miles per second. And obviously you're going to cover a lot less miles in a second than what you will in an hour. So fortunately what you see here is that we get a smaller number. So that's a good indication that we're on the right track. Okay, so that's, getting up there in difficulty. You'll have plenty of opportunity to practice doing this through the homework, and you should definitely do that. Other ratios that we're going to encounter in chemistry: concentration I mentioned previously, density, we've seen that in other videos. So it's probably well known that the density of water is 1 gram per centimeter cube. We're going to convert this to pounds per inch cube. So I'm going to have to convert this unit here to pounds, so the mass unit, and then the volume unit I'm going to have to convert from centimeters cube to inch cubes. So I need something that relates grams and pounds. So I had to go to a table and I found that equality. And then I have to relate centimeters, this guy, and inches. And I went to tables and I found this equality. And I want to be really mindful that don't forget that I'm going to need to cube my conversion factor in here. So we know the density of the water is 1 gram per 1 centimeter cube. And I'm just going to convert the top line first. So I need, in my conversion factor, grams on the bottom line and pounds on the top line. And from my equality, I got 1 pound for every 453.6 grams. So grams is going to go. And then now I need to get rid of my centimeters and turn them into inches. So I'm going to use my second equality. And as I mentioned, I've got to remember to cube my conversion factor or this isn't going to work. And according to my equality, I get 2.54 centimeters per 1 inch cube, 1 inch, and then that has to be cubed. So centimeters goes, centimeters cubes go, there we are. So that's looking good. The only things that are left are my pounds and my inches gets cubed. So yes, that's going to give me pounds per inch cubed. And there's my answer. And yeah, that's it. That's how it works. All right. So that's a pretty complex kind of problem. The very advanced unit conversion problems will involve derived units. You know how we have those things like pressure measured in Pascal? We said that that's a derived unit. Joules, which is a measure of energy, that's a derived unit. And you know, you're going to see these in the homework. These are significantly more difficult than any of the problems that you would have seen in Chemistry 139. So here's a classic one. It says a chemistry graduate student measures the performance Z of the new pump in his lab. So Z is just a letter that they're giving for performance. And it said the result is that the performance equals 17.4 megapascals per centimeter cube per second. And for some reason, you've been asked to convert this to kilojoules per second. So the very first thing that I do is I recognize that Pascal is a derived unit. And I want to know what are the base units that this is a combination of, right? It's not one of the 7 SI base units. And similarly, the joule, I know that the joule is also a derived unit. It's not an SI base unit. So I just kind of like, you know, put into Google, you know, Pascal derived unit, and then I went to the Wikipedia page and I got this little handy dandy equality that says that 1 Pascal equals 1 joule per meter cubed. And so that's my missing piece of information, isn't it? Because that's going to allow me to relate pascals to joules. So the first thing I did to solve this or to begin solving this problem was I recognized that I can just replace the uppercase M there, which is the decimal prefix for meaning mega, with the mathematical meaning, which is to multiply my number by 10 to the 6. So that's what I've done there. So I got rid of the M. And then the second thing that I wanted to do was to get rid of my centimeters to turn them into meters, right? So I want to turn my centimeters cubed into meters cubed. So I multiplied by this conversion factor here. And of course, I remembered to cube my conversion factor. And I know that there are 10 to the minus 2 meters in 1 centimeter. And that's going to get rid of my centimeters cubed and leave me with meters cubed. So I'm doing okay now. I just need to get this Pascal business into joules. And so to do that, I'm going to use the equality that I found on Wikipedia, or you could find it in your textbook as well, that says that 1 joule per meter cubed is equivalent to 1 Pascal. And what that's going to do is eliminate my pascals and leave me with joules per meter cubed. So we're getting in business now. So the cool thing is that meters cubed and meters to the -3 are going to cancel each other out. So that just leaves me with joules. So I would have at this point joules and seconds to the -1. So I'm really close. And I just got to go one step further, and that's to turn my joules into kilojoules. So what I'm going to recognize here is that kilo is just the decimal prefix. That means multiply by 10 to the 3. So now I'm going to multiply by the conversion factor of 1 kilojoule per 10 to the 3 joules. And that's going to get rid of my joules. And the only things that I've got left now are kilojoules per second, which is exactly what I was asked to do. And so once I've got all of that figured out, I put it into my calculator and I get my final answer. So what's going on in this problem? Why is this sort of like such a challenge? I think the first thing is that there's meant to be a minus sign there that I missed. So make sure you put that in. Why is this so difficult? Well, you've got a couple of things going on. You're converting a volume that requires that you cube your conversion factor. We've also got, we're doing a bunch of decimal prefixes in here. You can see that there's one there, and then we also did the whole thing with getting rid of the mega. But we've got decimal prefix in there. And then I guess the other big thing is that we used a derived unit, didn't we, right? So you've got like about 3 things happening in the one problem, and that makes it kind of tricky. Okay, so you probably recall that there's another type of conversion problem that we do that doesn't rely exclusively on conversion factors. You have to use formulas. And these are when we're doing conversions between different scales of temperature. So commonly in the US, we use 3 different scales of temperature: Celsius, Fahrenheit, and Kelvin. Now, I gotta say that I've never seen the Fahrenheit scale used in the chemistry lab, but I do frequently see Celsius and Kelvin used. Often we like to measure in Celsius because it just kind of gives us nice numbers that are comfortable. But then we normally use the Kelvin scale whenever we're doing any calculations. Now, to convert between these different scales of temperature, we're going to use formulas, not just straight up conversion factors. And it's for a pretty simple reason. Every measurement that we've looked at so far, everything that we've been interested in measuring, regardless of the units that we use, they all have the same 0 point. So 0 pounds is exactly the same as 0 kilograms, which is the same as 0 grams, right? They all have the same 0 point. 0 meters is the same as 0 kilometers, which is the same as 0 miles. So there's no difference in the 0 points. We know though, 0 degrees Celsius is 32 degrees Fahrenheit. The temperature scales have different 0 points, and we have to take that into account. So in order to convert between these 3 systems of temperatures, we're going to use these formulas here. And you can see that in each case, we're going to be like adding or subtracting a term, and that's going to account for the difference in the position of the 0 point. In the case of Celsius and Fahrenheit, we also have to multiply by a fraction, and that takes into account the different size of a Fahrenheit unit versus a Celsius unit. Okay, so let's talk about Celsius and Fahrenheit. Like I said, this is the least common one that you're going to be doing. The Fahrenheit scale is offset from the Celsius scale by 32 degrees. That is, 0 degrees Celsius is equal to 32 degrees Fahrenheit. So we have to take that into account. The other thing that we should recognize is that a Fahrenheit unit is a lot smaller than a Celsius unit. So for example, if you look at the difference between the freezing point of water and the boiling point of water on the Celsius scale, well, water freezes at 0 degrees Celsius, it boils at 100 degrees Celsius. There are 100 Celsius units between the boiling point and freezing point of water. Now, if we look at the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. That means that in the space that you have 100 Celsius units, you have 180 Fahrenheit units. That is, a Fahrenheit unit is only 5/9 the size of a Celsius unit or a Celsius degree. And so that's why we have this multiplier here in the formula. Now, the situation relating Celsius and Kelvin is quite simpler. They're quite a bit simpler. So I'm just going to skip over that example because it's not particularly relevant. The size of a Kelvin unit is the same as a Celsius degree, but the Kelvin scale has a 0 point that is offset by 273.15 degrees. So 0 Kelvin is minus 273.15 degrees Celsius. Now, the nice thing about the fact that it's only the 0 that is offset means that the temperature change on the Celsius scale is exactly the same as the temperature change on the Kelvin scale, because the size of a Kelvin unit and a Celsius unit are the same. So if something goes up by 5 degrees Celsius, it went up by 5 Kelvin. So you don't have to do any math. So what that means for us is to interchange between these two systems, all we have to do is add or subtract 273.15. So if I want to convert 37 degrees Celsius to Kelvin, all I got to do is add 273.15. So this is probably the most common type of conversion that you'll do, converting from Celsius, which is like what we like to measure stuff in, into Kelvin in preparation for doing some calculations, because we normally do our calculations using Kelvin units. All right, so you had a kind of a whirlwind review of unit conversions and scientific notation, but I think it's enough. You're going to have extensive opportunity to practice before you take your test and your quiz. So, in a pretty low stakes environment, the objectives that you're going to be solving problems in are, you just get graded for completion on that. So as long as you kind of work on it and figure it out, you'll be okay. You can use Google to check conversion problems. It can do some pretty complicated ones. It'll do those for you, so just to make sure you're on the right track. And also wolframalpha.com, and there are other websites as well, but those two are really kind of easy to use. Both those websites are great for checking your answers to unit conversion problems. Now, of course, you've got to kind of be able to show your work, and you later on when you're doing standardized tests and things, you're not going to be having access to a computer. So you should practice and make certain that you understand what is going on, because you're going to be doing this beyond this class. Okay, so that brings this review to an end, and I hope you found the video helpful.